All right, well, we will get started. We are live. So let me go ahead and share my screen. And we'll wait until Jeffrey gets back and Jason gets back. And I don't know if Elric's going to make it, but we'll go ahead and get started. Here we go. Let's see. I will make my this. Okay.
Is this going to be applicable to other aspects of my life, or
Is it going to be applicable?
yeah, is this information applicable?
I think this information is applicable, provided it's an instance of the type class applicative, which many things are, including array.
I think I met Ray.
What's that?
I think I've met Ray.
You met Ray? Yeah, this is just going to be a thing of life lessons to which you can apply to your existing life. So today we are going to talk about applicatives. And applicatives are a very handy type class that yeah, you can use for great good. My code examples and my slides are really in a half-baked state, so this is going to be very interactive, very discussion-based. So we're probably going to have to suss out the meaning of applicatives because I haven't done a very good job of illustrating them. But before we start with applicatives, let's start out talking about the review of functors. And because applicatives are, by their broader term, called monoidal functors. And we talked about monoids and we talked about functors, right? But these are weird terms. I advocate just saying the weird terms enough times so you just internalize them, because like I put on the README in Funkadelic, you know, the word, there's like a Finnish word called taskulampu. And that sounds really weird. Like you're like, what does it mean? Well, it means flashlight. It's a very useful and easy to understand thing that just has a strange terminology. Same thing with monoids and functors and applicatives and all that stuff. So functor is something that we use all the time. And that is something where you have a computational context or a structure and you're able to apply a function to it, and what the content of the computational structure changes according to the function, but the structure itself does not change. So this is kind of the generic thing where we've got a function that maps A to B, and we have A inside a computational context. We apply the function via map, and we have B inside the exact same computational context. So for an array, the computational context is that there is a list of things. Okay, so I have this array on the left, A, B, C. I'm going to apply some mapping function, and I end up with a array on the right that has the exact same number of elements. The computational context is preserved, the length of the array, but the content changes. So the thing that the analogy I like, it's the same building, different tenants. Right, so it applies to arrays. A tree is another example of a functor that you see, where the branching structure, the depth, the number of nodes, all of that is exactly the same. So when you're mapping, the tree on the left is the same as the tree on the right. The tenants change, the building stays the same. JavaScript objects, also functors. So here we have an object that has two keys, first and last, and we're just going to map it. It has the same structure, the same number of keys, the same name for the keys. It's just the values that are changing. And so what functor allows you to do is it allows you to take a function with one argument that just does the transformation. And so you end up with exactly the same computational context. Well, that's great, but what if we have a function that has multiple arguments? So an example of this is like addition, right? We want to take, like, capitalize takes one argument, right? I have an input string and output string. But what if I have something like add, and I want to do something like that? It takes two operands, and I want to add up the numbers of things that are contained inside two functors, right? So I basically want to do something like this. Like, let's say I have an array of 1, 2, 3, and another array with 4, 5, 6. How do I actually take and add up all those numbers without having to write a custom looping function, right? I mean, we can do this. We probably have done something like this. But really, we know a lot about the computational context here. We know a lot about the computational context here. We know, like, our kind of desired output format. And so is there a way that we can rationalize across that and be able to apply a simple function across multiple functors? And that's where the answer is yes. Of course, you can do that. And the answer is you use applicative. And so the way that you do this is and so this, unfortunately, this is where my slides stop. The end.
Off the rails.
Off the rails, everybody. So we just are going to have to explore it by hand. And what you end up doing is you end up taking an instance of your functor and putting the function that you want to add, or the function that you want to apply into the functor. So I end up having an array with the add function, and then I apply, there's this operation called apply, where you take a functor that contains the function and the functor that contains the values, and you collapse them into a single instance, which now has a new function that has the arguments from the second functor applied to that thing. It sounds more complicated than it is. And it doesn't really work unless you have currying involved. In other words, if I have a function with two arguments, in a language like Haskell, you can pass one operand and that returns a new function that has an arity of 1, and then you can pass the second operand and that actually gets you your value. And in fact, in languages like Haskell, every single multi-argument function is actually a set of single argument functions that return functions. So I take an argument, I return a function. I take an argument, I return a function. I take an argument, and then I return a value. And so that would be, yeah, that's how Haskell models it. And I don't have working code examples, but the show must go on. So what is this looking like in practice? Well, it means that you need, at this point, I might just like break into, you need some way of putting the function, putting the function into the functor, and then using that function inside the functor to apply, or to apply it to the values in the other version. So like, we can actually go to some code examples here, even though they aren't quite working. Oh yeah, I can fix that. So the way that you put a function into the box, so to speak, is with there are two methods defined on the applicative type class. There's pure, which is the idea that I can take any value and I can put it into the computational context. So given any singular value, I do what's called lift it into this computational context. So if I, let me probably, so okay, so like if I say f.pure1, because there can be multiple instance applicatives, I have to say what type of applicative I want to use. So like oops, I've got some debugging content in there. Hold on. Okay, let's try that again. So I say f.pure1, that gives me one value. If I say f.pure, that's going to give me, another value. So this is how you take any value and you put it into a functor. So you have to implement that. And if we look at the implementation of, let's see if I can. We look at the implementation of that in, let's see. For array, you can see it's pretty simple, right? So going back over here. So what we can also do is we can say f.pure, and then we pass it a function. So if we say like function add, like that. Let's see if we say f.pure. Say what type of pure context we want, because there's different pure contexts. There's arrays, there's trees, there's for the type of applicative that you're working with, you have to tell it. In a statically typed language, you wouldn't need that, because you would need to tell it what kind of pure context, because you would know based on the variable that you were assigning it to. So you can see I've got this function in there, and I can apply. If I say, I can extract the function, and I can say like 1, 1, like that. So if I add 1 and 1, it's there. Now I've got it's currying this function. So if I just pass one operand, it's going to return a function. Then takes one argument and returns a value. Does that? So there's a little bit of magic in there to curry that function, so that it can be applied incrementally. And so then, unfortunately, I have to do some hand waving, because then what you would do is you would call apply. You would take this pure, you would say like f.apply, and then we pass the pure value. Let's see, let's just say, this is like add array. We would say apply, pass this add a, and then we would pass it a list of arrays that we wanted to apply. So in this case, there was 1, 2, 3. Four, 5, 6. And what this will do, and again, like I said, I have to hand wave here, is it takes this function that's embedded in this array, applies the result to that array, which then now I've got an array of functions, and then it applies again to this array right there. So what you can do is if I have a function that takes 2 arguments, I can take 2 instances of the applicative and apply that function over them and get the applicative out that's the result. If I have a function that takes 5 arguments, I can apply it over the context of 5 applicatives and get 1 applicative, which is the result of applying that single function. And the power of that is like, I'm just using a simple add function, right? I don't have to worry about the computational context, because it could be an array, it could be an S3 bucket, it could be some set of microservices. Like let's say I have some, I need to do some sort of, some sort of search over 5 different places. I can define the function independent of the computational context, and I can apply it over there. And it can take as many arguments as I need. It just needs to have 1 instance of the applicative to satisfy every argument. And so again, in the same way that map allows you to apply a function, and like you can use the same function, which is just such a simple little thing, and you can apply it independent of an arbitrarily complex computational context. Same thing applies with applicative, which is where you have a set of dependencies in your computation. In other words, I need 5 inputs, and I want to draw those 5 inputs from 5 different applicatives. But those I don't want to worry about the computational context. I want to be able to add 2 values in an S3 bucket. I want to be able to add 2 values in an array. I want to be able to add, I want to be able to add the values in a tree. I should be able to do that by composing the add function with the thing that captures the structure that I'm working with. So like the example, I think what really did it for me was working with trees and being like, look, I can just define this applicative instance once for a tree, and that's the part that has all the recursion and like all the like kind of mind twisty stuff that like sucks with dealing with trees, where you're like, you have to like apply, you have to work with this node, then you have to work with your child nodes, and you have to recurse on down the tree. But you can do that once. You can do that once in the instance of applicative or in the instance of Funktoy, and then you can literally work with any function on that data structure, and you don't have to worry about, like, you've captured the concern of the structure. And so this code doesn't work. There's actually there's some work to do there. It actually has to do with, I wasn't taking into account that the native array map actually passes in like index, and like it fucks with the currying because it's like passing in 3 arguments instead of 1. Yeah. Any questions? I know this is it's a complicated concept, kind of. It's complicated until you have a good visual explanation, which I haven't written yet. Although there is some good reading out there there's actually a great resource that I found yesterday that explains a lot of this stuff, I think even in JavaScript. It's a adaptation of a visual thing that someone did with a Swift, in Swift, and I can't remember. I think I have, where did I was looking at it just, I found it just a little bit ago. Let me see. if I can find it. Here it is. So I will pull this over here. Oops. Yeah, so they've got a great, like, this is a great article. So talking about functors. So let's see. It's not, it's not, it's not the perfect explanation, but it does do a good job of saying, hey, I've got this function in a box. I apply it to this thing in a box. Like I take the function out of the box, the value in the box, and recombine them back into the box. And so I've got a new value back in the box. And so you can do this with multiple. This is +3, so it's one argument, but it's basically the number of arguments in the function is the number of boxes that you need to do it. But again, confusing thing is like, what is this box? Well, the box is just the structure that you're working with. And the reason it's valuable is so that you don't have to think about the structure. Because if you can implement this, if you can capture this once in the instance of applicative, you can decide like, what does application mean for arrays? Then you don't ever have to do it again. In the same way, if you can say like, what if I define what mapping is for an array, I don't ever have to think about it again. So did that help in any way? I'm seeing a lot of confusion. Like,
I understand more of it than I did 10 minutes ago.
okay.
Yeah. It's also like very similar to Funktoy. Like it's
because it still is.
because it is Funktoy. Yeah,
It is, right. So every applicative must also be a functor.
Is there a beyond the applicative view? Can we go further levels?
Can you go further levels?
The ultimate.
I think, well, so applicative is actually, I think applicative is actually a leaf node. There's probably stuff that it's built on top of applicative, but I don't think, like if something's, the next thing that we're going to talk about is monad, but I don't believe that monad is, yeah, no, it's not a requirement that something be applicative for it to be a monad. Yeah.
But an applicative is both a functor and a monoid, right?
It is a, it doesn't actually need to be a monoid, but it's monoidal in the sense that you have, what happens is you apply the function and you collapse it, right? So to review, I probably should have reviewed monoids in the sense that it's things that you can mash together and collapse. So like integers are monoids over the operation of addition. So I can take a whole list of integers and I can apply this operation and collapse them all, an infinite number or an arbitrarily large list of integers and get one integer. Like it's so it's the exact same concept as I have a list of functors and I'm mashing them together. And the way I'm doing is I'm rolling them up by applying this function. And then, so yes, it's that concept of smashing things together. As an interesting note, I did finally implement monoids inside Funkadelic. I haven't documented them yet, but for those interested, where did it go? Oh, here it is. Let's see. What's that?
thought for a minute those were all horizontal splits.
No.
Like,
So I think, so you can say, like I can mash arrays together. I actually don't think so reduce array. You take a list of arrays. So like 1, 2, 3, 4, 5, 6. And so a monoid is something that can be, a semigroup is something that can be appended together. And a monoid is something that can be appended together and has an empty value. So an array has this concept of an empty value, which is the empty list. So there you can see, and what I'm working on is like, there's monoids for, I don't, like there's no monoid for string yet, but there should be. So here's how you would actually implement this. Maybe we can, that would be fun, just to kind of show how you would do that. So you can say like hello world, like that. Right now it's using, yeah, it's using, what it's using is using object, the object instance for monoid. But what we can do is we can say,
It just like splits it out each character
as a key, yeah. Well, because it's basically, yeah, it's actually using the array properties, I think. I don't know. But what we can do is we can define an instance of monoid for string. And then we can say, so the empty value of string is that. And I think that's it. Yeah, that's all we need to turn a semigroup into a monoid. Now, it still doesn't work.
Yeah, that's using an array. Yeah.
Huh.
And then like,
No. We also need to define, I'm sorry. We also need to define a semigroup. Because what it's using is now it's using the empty string value, but it's using, for append, it's using object append. Because object is also a semigroup, and it just takes it's the equivalent of object assign. So this is actually an interesting thing, is like when you realize that object assign, which takes an arbitrary number of objects, is really conflating semigroup and monoid. And so where actually, no, it's, yeah, it's kind of halfway between object and monoid. So let's do the implementation of append of semigroup for string would be return, what is it, a.concat b. I think. Now let's try it. Yeah, there we go. So if you have an append operation and you have an empty value, you now have a really simple way to reduce things. And so ideally what I'd like to get to is being able to say f.reduce and then have kind of stand-in monoid classes that automatically like wrap things. So you should be able to see, like, you should be able to say sum and then pass it a list of integers. 1, 2. Something like that. And so then it'll know, like, I want to do summation on this list of things instead of you having to write a fold function by hand. Anyway, that's off the path of applicatives. But it's inside the same vein. So interestingly enough, functions are also applicatives. And so, but what's interesting is the pure, if you take, so you can think of, so you're all familiar with apply in in JavaScript function, like, you know, function.apply, right? It takes a list of arguments and then returns the value. So that's actually, you can define an instance of applicative. It's generalizing that concept, really. And a function is also a functor. And the pure, yeah, I know, it's kind of crazy. But the pure value for a function, like the way to lift any value into the context of a function, is just like the ID function, right? X returns X. Like you pass it X, it returns X. You've now lifted that value into the computational context of a function. And so then you can apply a function to a list of functions who also take the, so what you can do is you can take a function and you can put it in the pure context of a function, which is a function that returns that function, and then apply it to a list of functions who all return a single value, which are the arguments to the functions, and that's function application. That's the instance of applicative for function. And so, yeah, it gets a little bit.
Yeah, that got pretty hairy.
Basically, like, yeah. But I guess the reason I only brought it up is that these concepts do, like, we have the concept of application for functions. It's just generalizing it for any type of structure, not just a function. So we can programmatically apply a function to a function, or we can programmatically, yeah, apply the arguments of a function. Well, you can programmatically apply you can source the arguments of that function from anywhere, and this is how you do it, not just by providing the values to apply. Maybe that's a good tack to take. I don't know. Have y'all worked much with like function.apply in JavaScript? Nope. Not much.
I used it, but I looked it up and I used it, and then I forgot about
Right. Yeah.
Okay, so
as with most things.
so the way this works, and this is a native JavaScript capability, is like, let's take our add function, right? We still have that, right? Okay, function add. Right, so you can say add.apply. This is one way to call it. We'll add 1 and 1. But we can also say add.apply. And then, no, because you have to pass everything of this every function in JavaScript has this context, so just ignore that. And then you pass a list of values. Right? And so really what this is like right here, we're passing in just hard-coded values. And so applicative is really just letting these values come from anywhere. Let them be embedded in any computational context. And the context is responsible for extracting the values and putting them back in. And so that's like, maybe that's a better way, like, it's like, it's a generalization of this whole process of abstracting function application across any data structure. Yes, 5. Like. Any other questions? Obviously, I've got some work to do on this. I realized actually when I picked it, I thought applicative was going to be easy, and this is actually, I think, the hardest one. It's harder than Monad, in my opinion. Even though it's generally introduced first, it is weird.
It's a bit weird to wander into a series on functional program primitives.
Yeah, not having to like, yeah, because we context of Funktoy and Monoid, and what was the other one we did? I can't remember.
So Funktoy would be the array. in your example of add, but you had 2 3-element arrays. So is the fact that it's 3 elements, is that part of the functor?
That is part of, so for array, it's all about structure, right? The functor is about capturing the structure. So the structure of an array is the n-ness of the array. Like the length of the array, that's what defines the structure, right?
Right, because something that was expecting to use a value, this array,
right,
should be able to use the result of something you've applied to it. So if it was a different length, it would change.
Right. So if it was,
so the number of elements in the array is part of the functor.
Yes, it's part of the yes.
But you only had a singleton array of the add function.
Yeah, you know that's a good pickup, because what actually happens for applicative, you can do if like you so let's say so what happens then if I have that's the simplest case. What happens if I have 2 functions inside my applicative? Well, what I'm going to do is I'm going to apply the first function and reduce it across all of the arrays. Then I'm going to take the second one and do it across the same arrays, and then I'm going to concatenate those 2 arrays together.
What was confusing to me is that if the length is part of it, the functor,
right?
And your
well, so remember, functor and applicative are 2 different things. Every applicative is also a functor, but not the other way around. So apply is a different operation, and you're going to end up with different. It's not like what defines a functor is that you can map over it, right? So the map operation always takes an array of 3 and returns an array of 3. A map over a tree of 2 children always returns a tree of 2 children. So that's what makes a functor a functor.
Well, I guess what I would get was like why we were putting the function into an array when that singleton array with containing a function is still not in the same computational context as the input and the output.
Well, because that's that's different about applicative, right? They don't have to be in applicative. There's multiple computational contexts. You have multiple arrays. So you have multiple arrays within. So each array has its own computational context. So they don't have to be uniform. Like the output of apply does not have to be like, because it's got you could have an application that goes across 10 arrays. So it's gonna the output's gonna look a little bit different. Whereas a map always there's one computational context that yields the same computational context. Application doesn't necessarily work that way. Yeah. But within application, you are going to be doing some mapping. Right? Because what you're doing essentially with each, you can think of application as like reducing, of like you've got like 5 things and I'm going to mash, 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 mash. And so like at each mash step, I'm going to take the function out and I'm going to map it. Right? Now the mash can do like if you've got a functor like just, which is, a rake is kind of, the array's a tricky example because on the one hand, it's something that everybody's familiar with, like everybody knows array map like the back of their hand. But it also introduces some complexities. Like what if you're applying, because it's totally valid, you can take an array and put 2 functions in it and then apply it across a series of arrays, and what happens then? Or what if I take 5? You're basically doing like you end up doing like cross products, and you can do some pretty crazy linear algebra shit, right? Like that's a possibility.
Right. So it's part you take the function out, and then
right.
do that. So it's like, okay, if you now it's a tree instead of an array. So
No,
so why does it have
You're-
to be in the context?
you're always going to end up with this. Like you're always going to end up with an array. It's not gonna. You're not gonna like. You're not gonna. If the primary applicative that you're working with is an array, you're going to end up with an array. How you combine them is up to the definition of apply. But think of it as like one function for now. Like, how about this? Promise is also a functor. That's maybe, right? It is. It's just instead of calling it, the map is the then. And so you're taking basically the computational context is a future value instead of a length of things, but it's you're mapping the value inside that future value to another future value. And so, but the computational context is the same. But there, we're dealing with singular things. So imagine now you could do the same type of application where I've got, let's say I have that probably is a good example to use. Let's say I've got 5, I want to add two values. I could take the add function, lift it into a promise, and then apply that across 2 promises to get a promise that yields my final value, which is the value of the first promise plus the value of the second promise. Right?
Sure.
Yeah, that sounds like something that I might actually do at some point. Yeah.
Right. And then you don't have to worry about the endness, right?
Right.
But like, yeah, like, I'm trying to think of, yeah, if you've got some kind of standard library of functions that take, multiple arguments, you might want to have to always do, then, whatever, and kind of sequence it, but just say, hey, I want to take these 3 AJAX requests and just apply this function to them. That maybe is a better example. It's like I've got 3 values on the network, and I need to like fetch them, and I need to apply, a function to them. But I don't want to have to worry about like doing a one-off sequencing in terms of the promise. I can just say, hey, these things are instances of applicative, and I want to apply this function, this 3-argument function, to these 3 AJAX requests. Then you don't have to worry about, like, the computational context is still the same. You're like,
I'll read that Medium post.
That's a nice looking picture.
It did. Some of the stuff is like, huh?
No, really?
What's that? Yeah.
Yeah, but it's just like, okay, so I've read that Medium post, and I've gone through and a few more tutorials. I've picked up Haskell. I've got like a solid grounding in functional programming, whatever else. And
I think actually,
after I do all that, I'm still going to look at an actual program that uses a lot of this, and it's just got so much information content in it. It's going to be like those situations where you see there's a promise, and then you have like 3 arrows because of these nested functions, and you have to stare at it for a bit to see what it does. It's like, okay, now let's take that and generalize it to all of programming.
I think, well, yeah. I mean, the thing is what you do have to like. What it's about is you do have to like stare at the code and be like, and let your eyeballs unfocus and like see the stereo vision thing, but you only have to do that once for the instance of Funktoy. Like that's the thing. That's what's freeing and ultimately powerful about it is like if I understand how the Funktoy works for a tree, then I don't have to worry about it. I don't have to let like recursion get into my code anywhere else. Right? I can just say, oh, I'm mapping the values over this tree. I see this tree on the left. I see this tree on the right. And it's flattening the computation to say, okay, you're mapping this function across this thing. Even though that function in reality is fanning out across maybe 10,000 nodes and it's doing all this stuff, I can really just not worry about that and say, look, this is what I want to do.
Yeah,
it allows
the pattern matching becomes easier.
Mm-hmm. Yeah, exactly. And I also compare it to like with these fundamentals, like we generate so many throwaway abstractions. Like think about one of the things that's nice about REST, I know we've been like doing GraphQL all week, but like one of the things that's nice about REST is that it is a constrained model for modeling all of your operations, right? You have 4 verbs, 5 if you're using Patch, and you're very elegantly able to model all of these transformations, especially like gets based on, you know, this one set of things. I think by contrast, how often do we think, oh, array.map, promise.then are really the same operation and the same things, they can be composed in the same ways. But we don't, because we've created a one-off abstraction and not unified promise.then and array.map. And so we have to think about them in different things. But if we abstract that and say, oh, what I'm really doing is applying a transformation across a computational context, whether that context is, you know, a list or whether that context is a future value, the fundamental operation of map is the same. And I can, you know, any way that map can be composed, I can then compose it anywhere. And I don't have to have a separate set of functions for composing promises and a separate set of functions for composing arrays. I can use one set of functions. So your API, like the surface area of your API is like a lot smaller. It's convention over configuration for composition. It's like, I think I'm starting to think of like this type class system as being Ruby on Rails for composition, right? It's like we have these conventions for how to compose functions, and if you stick to them, you get all these added side effects. Like anything that operates on a functor, I just implement, like there's this whole, like if you look in like Haskell land, there's this whole set of libraries and everything that's like, if you define a functor instance for like your class, then you can do all these things for free. You know, like just boom, here's 1,000 functions that you can use to do all these really handy, awesome things with your shiny new data type, right? Versus having to like manually implement them every time. Or you could think of it like you know, like a microservices architecture. I don't know, would be another thing. It's like I can just implement my module, and if I implement my module using these set of interfaces, then I can plug it into this greater thing, and I get all these benefits like authentication and instrumentation and, you know, whatever, because I've conformed to this interface. And so it turns out that there's actually a very small number of these interfaces, and you can do pretty incredible things with them. Anyway, that's my spiel. All right. Well, unless there's anything else, I'll call this one, and yeah.
That's applicatives.
And that's applicatives. I got a lot more work to do, guys. Thank you for being guinea pigs. And I hope that you actually did come away with more than you started with.
For sure.
All right. And it's a wrap. Let's see, where actually is